All right, let's get going today. So today we're going to move into Chapter 8 after getting through some things, and I messed up this stuff, but I'm going to deal with that later. All right, so we have the first thing I want to talk about today is a quick highlight of the exam results in case you're curious. So here's what it looked like. Our first midterm, we had an average of 13.1 out of 20, and in line with what happens in a typical semester, the average was lower on this one, so we were at about 11.5. This number here is maybe not 100% accurate because when people drop the course, they disappear from Blackboard, and I don't have record of them anymore, so that might include, the average might be a little bit different than that based on some people that have dropped recently, but it should be pretty close to the right number. It's a little bit lower than last year, about 1% lower in terms of a percentage, but nothing I think to be concerned about. And we did a little bit better than the other sections did on average by about 3 or 4%. All right, so that's where we stood. I've been talking to a lot of people about their results, so if you have any more questions about how you did on the exam or what your current standing is in the course, I'd be happy to address that with you. But we do need to get on to the things we're talking about. So what we're going to talk about today first is it's a topic that goes way back to Chapter 3, so but it's very closely related to all the stuff we did in Chapter 7 with enthalpy and Hess's law and all that stuff. So if you're following along in the book, this one is actually Section 3.4, I believe. But your book presented this at a time when we were very ill-equipped to handle it, in my opinion, so we've decided to move this into Chapter 7 now, which is a lot more appropriate time to talk about this stuff. All right, so that's what we're going to do is starting out with talking about ionic bonding again, but again, as you'll see, a lot of the approaches we're going to use are related to enthalpy and related to Hess's law and things of that sort. Okay, so we have first thing we need to talk about are steps that are involved in ionic bonding. So reviewing back about what we're talking about there. And what we're doing we have, here we're considering KCl as an example. And we know from when we talked about this before that the metal gets ionized, it loses an electron, and then the non-metal gains an electron, and we form an ion pair that are then attracted to each other. So we have these two different ionization steps. So if we're talking about gas phase atoms, let's start with that scenario. Again, the metal loses an electron to make a positively charged cation. And as we talked about in Chapter 3, this step here, the delta H for this is what we refer to as the ionization energy of the metal. So we learned about ionization energy separately. That's what this delta H would be for this step here. And in this particular example that I'm using, KCl, or for potassium, that would be 419 kilojoules. So that's the delta H for losing the electron from the metal, and then the non-metal gains an electron. So a gas phase chlorine atom gains an electron to form Cl-. And the delta H for this step we refer to as electron affinity. So remember, when an element gains an electron, the energy change associated with that is electron affinity. So the electron affinity would be the delta H for this second step here, which is minus 349 kilojoules. And then as we now learned in Chapter 7, if we want to find what's the overall energy for this process, the process of taking potassium and chlorine and making K plus and Cl minus, we can add the two equations together, and then we can add the two delta H's together. So if we put everything together, gas phase potassium plus chlorine goes to K plus Cl minus. The electron here cancels out as an intermediate when we add these two equations together. And then the delta H for this process would just be the sum of the two delta H's, the ionization energy of the metal, potassium, plus the electron affinity of the nonmetal chlorine, which is plus 70 kilojoules. And something you'll talk about more detail in Chem 2 is that most processes that are favorable have negative delta H's. This one has a positive delta H. Its energy increases, and most things that happen in nature involve decreasing the energy. There's more details than that, but we'll skip those for now. But the point is that the formation of gas phase ions is unfavorable in most cases. All right, so it's unfavorable to form these gas phase ions. So then the question becomes, why do ionic compounds then form at all? You know, if the formation of the ions requires us to put energy into the system, why do these ionic compounds form? Because we know if we mix potassium and chlorine together, they're going to form potassium chloride. So why does this happen? And this comes then into some other processes that are involved with forming ionic compounds. So we're not just going to form the two separate ions, but once we form those two separate ions, there's going to be an electrostatic attraction between them. So this ionic attraction is an electrostatic interaction between the oppositely charged ions. And anytime we have an attractive interaction between two charged particles, which we've learned about way earlier on in the course also, this is going to release energy. Or the delta E, delta H, however you want to think about it, is going to be less than 0. So when these two ions come together and they feel that attraction between them, that's going to release some of that energy that was required to then form the ions. So if we do this in the gas phase, K plus plus Cl minus, and then two of these come together to form an ionic bond, a gas phase KCl. This delta H is hard to measure because ionic compounds don't typically exist in the gas phase, but it's around minus 500 kilojoules. So even forming one interaction between a positive and negative ion releases a lot of energy. So it's a very energetically stabilizing process when you form these interactions between negatively and positively charged ions. But the one that's more relevant to us is what happens in the solid phase. So as we know from our most familiar ionic compound, sodium chloride, just about every ionic compound, I think, you know, everyone that we would ever talk about in this course, they exist as solids. So the ions come together and they pack into a solid arrangement, and we'll talk a lot more about the details of those structures in Chapter 9. But for now, what we should keep in mind happens is that these gas phase ions, if we form them, they're not just going to form a single attraction between two ions and stay in the gas phase. They're going to form an extended solid KCl in this case. And the way this looks in very low detail for now, that we'll get to, as I said later, is you form these arrays of positive and negative charges that are all sort of lined up in all directions. So you don't just get interactions between two ions, you get interactions between a bunch of ions in all different directions. And so what we're interested in then when we're defining the formation of ionic compounds and this attraction between the ions, that's a very strong, important part of that. What we're interested in is this term here, the gas phase ions reacting to make this solid, and this is what we call the lattice enthalpy. So the delta H of this process is called lattice energy or lattice enthalpy, abbreviated as delta H lattice. And this is always going to be a large negative number, as we'll see. So this term here, this attraction between gas phase ions to form a solid ionic compound, as I said, is one of the most important factors for the formation of ionic compounds. And we want to know, how do we actually determine what this value is? All right, because this value is defined, again, as the amount of energy that's released, the amount of heat that's released when ions come together to make 1 mole of an ionic compound. How do we determine what the value of this is? And this is what we're going to learn today. It's referred to as a Bornhaber cycle, but really what it is just a huge application of Hess's law. So we've been talking about Hess's law in Chapter 7, which is the idea that we can add together multiple chemical equations, and then we can find the delta H by adding up the delta H's as well. And this is an application of that allows us to find lattice energy, because there's not really a great way to measure this directly. It's hard to go into the lab and make gas phase K plus and Cl minus, and then to directly measure the amount of energy that's released when those two come together. Not a particularly straightforward thing to do, but there are a lot of other enthalpies that we can measure, and we can combine those to determine then what the delta H is for the formation of this ionic compound, the lattice enthalpy. All right, so here's what we're going to get into now, is what's called a Bornhaber cycle. So what we do in a Bornhaber cycle is it's a series of steps. As you'll see, in every case, it's going to be usually about 6 steps or so. So more than we've been dealing with, but not a huge amount. And the key thing here, the reason why we call it a cycle, is that we begin and end at the same place. Okay? And we begin and end with an ionic solid. Now, there's a few different ways of drawing these Bornhaber cycles, and I think the way that I do it is hopefully the easiest to understand. But the point is that when you go around this whole cycle, when you start with the ionic compound, you do a bunch of steps to break up the ionic compound, then a couple more steps to form the ionic compound back again. This whole process has a delta H of 0. So you're going to be adding up the individual delta H values for all these individual steps, and the sum of all those will be 0 because we're starting and ending in the same place. Okay, if you're starting and ending at an ionic solid, the delta H has to be 0 because there's no change in the system. And so what this is, as I said, it's an application of Hess's law. But the difference here is typically we're going to know that the overall delta H around the whole cycle is 0, and we're going to be solving for one of the unknown enthalpy changes, usually the lattice energy. So we go around this whole cycle, the sum of all the delta H values around the cycle is 0, and we have one unknown, which is our lattice energy that we solve for. Okay? And the way we typically arrange the Bornhaber cycle is that there's going to be some steps in our cycle that have a positive delta H. So we're going to put those on one side. And then we're going to have, and this is what you need to be able to visualize the cycle. It's not always important to do that, but there's an equation that comes out of this also. And you're going to have steps with a negative delta H on the other side. So as we go around the cycle, we do a bunch of steps that increase the enthalpy, then we do a bunch of other steps that decrease the enthalpy back to our starting point. The sum of all of those has to be 0. And so we just add them up and set them equal to 0. And solve for whatever unknown we have, which is usually the lattice enthalpy. Now, before I get into all the details of this, I should warn you that this is the topic in my admittedly short career of teaching chemistry of about 3.5 years now that, generally speaking, Chem 1331 students hate this the most. But I don't want that to discourage you. I just want you to be aware of that these Bornhaber cycle lattice energy problems are that some people find them to be painful. But I'm going to try to teach you the method for doing this. By understanding the method, you should be able to apply it to any situation. And I think it's another one of those things. The more you practice it, the less daunting it seems. All right, so here's what we're going to go through it now. But before we set up a Bornhaber cycle, there's some other energies that are needed. So we reviewed ionization energy and electron affinity. Those are 2 of the steps that are going to occur in our Bornhaber cycle. Then there's some other ones as well that we need to either review or talk about. So one of them is formation enthalpy. This we know all about because it was one of the chapters covered or one of the topics covered in chapter 7. So in the formation, as we talked about, it's a compound forming from the elements. And delta H of formation for many compounds is tabulated, so this is going to be a parameter that we're always going to have pretty easy access to for setting up a Bornhaber cycle. And then obviously in a Blackboard problem we would give you this number if you need it. And so for potassium chloride, which is the example we started working through already and we're going to finish up now, the formation enthalpy is defined as the formation of the compound from its elements, and it's going to be 1 mole of compound, as we said. So this is the equation that's associated with the formation enthalpy, and delta H of formation is, in this case, minus 437 kilojoules. That's specific to this compound. Then there's one other step, and this one we haven't seen yet. We're going to talk about phase changes a bit more in Chapter 9 as well, but for now what we have to include this here is what's called atomization sublimation. And the reason we need this is because, as we'll see, we include the formation equation as part of our Bornhaber cycle. That involves the metal in its standard state, which for every metal except for mercury is a solid. So here we have solid phase metal, but we know then that the ionization energy of the metal is defined for the metal in its gas phase. So before we can include the step that involves ionizing the metal, we have to take the metal from the solid to the gas phase. That's going to be a separate step in between those two, which means we have to take what's called the atomization or sublimation energy which is the amount of energy required to take 1 mole of a solid metal and change it into gas phase metal. So it's called either sublimation or atomization. And again, that step is important because the ionization energy step for the metal comes from the gas phase of the metal. So we have to do this as part of that. So this delta H is going to be sometimes abbreviated as delta H sub for sublimation. And so sublimation is the process of going from solid to gas, as we'll talk in more detail about in chapter 9. And for potassium, it's going to be plus 89 kilojoules. And really for any metal, it's going to be a positive number. It always requires us to put energy into the metal to get the atoms to separate and go into the gas phase. Okay? So that's atomization or sublimation. And then the last one here that we need is bond dissociation. We've already learned about this in chapter 3. This is the energy required to break a covalent bond. And the reason we need this is because for the nonmetal part of our ionic compound, as we talked about last week, most nonmetals on the periodic table are diatomic in their standard state. So when we do the formation equation up here, we're forming the nonmetal in its standard state, which is often going to be X2, so Cl2, F2, O2, and so on, or sometimes higher than that, like S8. So you're forming the nonmetal as a polyatomic, and if we're going to do electron affinity step for that nonmetal, that refers to a single atom by itself, so we have to break the bond between the two nonmetals as it exists in the standard state. So for this one, we have to take Cl2 and break it up into chlorine atoms. And so bond dissociation is the enthalpy change associated with breaking 1 mole of bonds. We saw that in chapter 3 already. So this delta H is referred to as the bond energy. Has a few different names. Bond dissociation energy, or sometimes just delta H of dissociation. So a couple different names for this, but it's equal to the amount of energy required to break a chlorine-chlorine bond, and in this case is plus 244 kilojoules for Cl2. Okay? So these are the other 3 terms we need. We talked about already lattice enthalpy, we talked about ionization energy, electron affinity. All of those are part of this Bornhaber cycle that we're going to build. These are the other 3 terms. So let's just make sure we understand what they are before we go into it. So now let's go ahead and then build our Bornhaber cycle. So I've drawn a little template for myself so that my inadequate artistic skills don't reveal themselves on this slide. There's a lot of things to put in here. So what we're going to do, as I said, in a Bornhaber cycle is we're going to start and end at the ionic solid. So here we're doing it for KCl. So that's going to be the bottom here. We're starting and ending at KCl solid. And then what we're going to do in this cycle, as I said, is we're going to go around through a bunch of different steps that are going to first break the ionic compound up into its ions, and then they're going to reform the ionic compound. And the energy associated with reforming that ionic compound from the ions is what we refer to as lattice enthalpy. So on the left side, we're going to put all the steps that require positive delta H, that require us to put energy into the system. So the first thing we're always going to do is we're going to take our KCl and we're going to break it up into its elements. Okay, so the first step is going to take KCl and break it up into potassium solid and then 1/2 Cl2. So elements in their standard states. The standard states for chlorine is Cl2, so we form 1/2 Cl2 to keep everything balanced. There's only 1 chlorine atom in the formula. And this step is related to delta H of formation, but it's the opposite of that. If we go from the compound to the elements, we're doing the opposite of the formation enthalpy, which means that this term here is going to be minus delta H of formation. So remember, if we flip the order of the reaction, if we flip reactants and products, we change the sign of delta H. So delta H of formation will be going from elements to the compound. In this case, we're going from the compound and we're breaking it up to its elements. So that's why it's negative delta H of formation. And this is always going to be the first step in a Bornhaber cycle. This will be invariant for any Bornhaber cycle you put together. You're always going to do this step, and it's always just going to be negative delta H of formation, never going to be modified in any other way. So for this compound here, we saw that the delta H of formation was minus 437 kilojoules, so the number associated with this step would be positive 437. All right, so it requires us to put energy in to break it up. Then the next 2 steps we're always going to, and again, you don't have to always do these in the same order, but I like to keep them in order so I don't forget anything. The next 2 steps is going to be associated with the metal. So the 2 things we have to do to the metal before forming the ionic compound back from the ions is we have to take the metal from a solid phase to the gas phase. So that's referred to as the atomization or sublimation energy. So we're going to take this Ks, this solid potassium, and change it into gas phase potassium, doing nothing to the chlorine for now. We're doing one step at a time. This step here, as we said, is referred to as the sublimation enthalpy or atomization enthalpy. And as we said, for potassium, it's 89 kilojoules per mole. So it requires 89 kilojoules a mole to go from solid phase to gas phase potassium, and that's going to be the next step in our cycle. And the reason, as I said, that has to be the next step is because what we want to do is we want to form gas phase potassium ions, but the ionization energy for potassium is defined exclusively in the gas phase, so what we have to do now to make the K plus gas and lose an electron from that, and we still have the 1/2 Cl2. Okay, and this step here, as we said, is referred to as the ionization energy. The first ionization energy of potassium, and it has a value of 419 kilojoules per mole. Okay, so again, the two steps associated with the metal. After we break the ionic compound up into its elements, the next two steps associated with the metal are going to be invariant. We're going to sublimate the metal from solid to gas phase. Make it obvious that that's a G. And then once we have the gas phase metal, we're going to remove an electron from that to form the gas phase cation for that metal, and that's going to be referred to as ionization energy. So those are the two steps associated with the metal. And then we have two steps associated with the non-metal that are going to occur in this cycle. So the first thing we need to do is we need to take our Cl2 and we need to break it up into chlorine atoms. So if we take 1/2 Cl2 and we dissociate it into chlorine, we're going to get, we still have our K plus and our electron. We haven't done anything with those. And what we're doing in this step is we're going to break up Cl2 into chlorine, so we're going to get 1 mole of chlorine atoms. So we have 1/2 mole of Cl2, that forms 1 mole of chlorine. We have to keep everything balanced as we go around. And this step here is the dissociation enthalpy. But remember that the dissociation enthalpy for Cl2 that we gave you is for 1 mole of Cl2. In this process we have 1/2 mole, because you have a coefficient of 1/2 in front of Cl2. And as we talked about, if you change the coefficients by 1/2, you have to also change delta H by 1/2. So this step here is going to be 1/2 times the dissociation enthalpy. And so the dissociation enthalpy for chlorine was 244. Yep, it's right up there. And that's going to be then 122. So we take 1/2 of that number, 1/2 times the dissociation enthalpy, because we have a coefficient of 1/2. So if any of your steps have coefficients, you have to modify the delta H by that amount. Okay? And then finally the exothermic steps on the right side. So the one exothermic step we have is we're going to take this electron and we're going to add it to the chlorine. And so when we add an electron to this chlorine atom, that's going to be referred to as electron affinity. So we add the electron to chlorine, that gives us K plus and Cl minus. And the step of adding 1 electron to chlorine is referred to as its electron affinity. We have 1 mole of chlorine in our equation, so we don't have to modify the electron affinity by any number. And that number, as we said, was minus 349. So that's the electron affinity of chlorine. And then the last step here is we take these two gas phase ions and we recombine them to make KCl solid. And that step here is what we refer to as the lattice enthalpy, and that's going to be our unknown value that we're going to solve for. Okay, so this last step, once we have the ions, once we have the metal cation and non-metal anion, we recombine them to make the solid ionic compound. This last step here is lattice enthalpy. So we've gone all the way around the cycle. We started at ionic solid, we broke it up into the ions using a number of steps. We recombine those ions in the last step. And so what that means is as we go around this circle here, the sum of all the steps has to equal 0. Okay, so 0 is going to be equal to all of these numbers added together. So 437 plus 89 plus 419. Bad thing when you hit that by accident. Plus 419 plus 122. And then we have a plus minus 349, which is the electron affinity term, plus the lattice enthalpy. And so that's our equation that we're going to solve. 0 is equal to the sum of all of those numbers. We just have to solve for our unknown, delta H lattice. Okay? And so lattice energy is going to be then, numerically speaking, when we solve for it, minus 718 kilojoules. Alright, so that's the amount of energy that's released per mole when K plus and Cl minus in the gas phase recombine to form KCl solid. That's the number we're interested in. Alright, so it's going around the whole cycle and setting everything equal to 0. And that gives us then the lattice energy. Alright, so as I said, it looks kind of daunting when you first see it, but we'll do more of these. Hopefully they'll get more familiar. So we're going to just work through one more example of this, and then I'll set you loose on the homework to try it yourself. So let's do it for MgBr2, magnesium bromide. So the way that these are going to often be set up is we're going to ask you to find the lattice enthalpy, and we give you a bunch of other terms that you're going to need to solve that. So we give you the sublimation energy, ionization energy. In this case, we need vaporization as well, as we'll see, dissociation, electron affinity formation, all these different steps that are going to be involved in our cycle to find the lattice energy of magnesium bromide. Okay? So looking at the numbers here, this is what we have. And so one thing to look at here is there's a slight difference here. In this case, it's MgBr2. So our metal is has a 2+ charge instead of a 1+ charge. So it doesn't change how you treat the numbers, but we have to be familiar with here is that if we're forming a 2+ cation, we're actually doing 2 ionizations. We're ionizing magnesium to magnesium plus, and then we're ionizing magnesium plus again to make magnesium 2+. So really this number here that I'm giving you, 2187, is a sum of 2 ionization energies. And it is possible we could give those to you separately. So if you're forming a 2+ cation, you need to have 2 ionization energies. And if you're forming a 2- anion, you'd have 2 electron affinities as part of your cycle. But it really gets added in the same way. It doesn't change how you do the problem. It's just that you have sometimes more than one of those occurring in the formation of your ionic compound. All right, so these are the numbers. Let's put it all together into a Bornhaber cycle. This one I'm going to try to draw by hand, so it'll probably be a mild disaster. Okay, so at the bottom of our cycle we have MgBr2, which is our solid ionic compound. And so then what we put into the cycle is, the first thing we do, as we said, is we're going to break this up into its elements. We're going to break it up into its ions eventually. So we're going to take our MgBr2 and we're going to break it up into the standard state. Sorry, there was an insect of some sort up here that bothered me for a second. Alright, so we're going to break up break up the compound into its standard state elements. So that's going to be, for the metal, a solid always, and this is mercury. And then for the non-metal, we have to think of the standard state of bromine. So bromine is also diatomic, Br2, and it's a liquid. So that's the one difference here, is that our standard state for our non-metal in this case is a liquid instead of a gas. We said that bromine is one of the 2 liquid elements, the other being mercury. So we have, this is the first step, which is going to be minus delta H of formation. So this is the negative of the formation enthalpy of this compound. And so if we go back up to the given information, the formation enthalpy is minus 524. So that means this first step is going to have an enthalpy change of positive 524. 524 kilojoules to break it up into its elements. And then, as I said, there's going to be 2 steps associated with the metal. We're going to sublime the metal or atomize the metal into the gas phase, and then we're going to ionize it. So we're going to do this step here where we take the magnesium solid and make it into gas phase magnesium, doing nothing to the bromine yet. This step here, as we said, is called the sublimation enthalpy. So that's just the energy required to break up solid magnesium into gas phase magnesium, which is this term here, plus 148. So it's 148 kilojoules per mole to do that step. The next step is the ionization of magnesium, and we're going to do this we're going to combine 2 steps into one here, because as we said, this is going to form magnesium 2+, and that's going to release 2 electrons, not touching the Br2 yet. So this is really the sum of the first 2 ionization energies, IE1 plus IE2. It's the sum of 2 ionization energies because we're removing 2 electrons. However, as we said in this problem, the way that it's given to us is we're giving one combined value of 2187. So that's the sum of those 2 ionization energies. The amount of energy required to go from magnesium to magnesium 2+ is given to us directly as plus 2187. And then, as we said, there's going to be some steps associated with the non-metal. Now the one difference here is that we see that our nonmetal here is in the liquid phase, and we see that the dissociation enthalpy, which is normally the next step, is for Br2 gas. So dissociation enthalpies are typically for gas phase diatomic elements. So we need to first take our bromine liquid and convert it into bromine gas, and that's going to be this step here, the extra one we had to add, which is vaporization. I don't think this will come up much, but I just wanted to show you that there is some variation in how these can be set up. So we do need to take our nonmetal also into the gas phase. So if the nonmetal is not in the gas phase in its standard state, you have to do a step to accomplish that. So our Br2 liquid has to become Br2 gas. And this step here, as you said, is called the vaporization enthalpy, which for Br2 is 31 kilojoules per mole. All right, we have one Br2, so we don't have to modify that number at all. And that's the amount of energy required to take Br2 into the gas phase. All right, and then the next step is going to be dissociation of Br2 into bromine. So we're going to go up to the top here, our last endothermic step, which is Mg2 plus 2 electrons, and then we're going to take this Br2 and we're going to break it up into 2 bromine atoms. So we've broken the bond between the 2 bromines. This, as we said, is referred to as the dissociation enthalpy, or the bond dissociation enthalpy. And for Br2, it's this number here, 193 kilojoules. So that's the amount of energy required to break the Br-Br bond. So we've succeeded in breaking this up, and then the last step is we have to get the bromine into Br- anions. So this is going to be our electron affinity step here. So we're going to take these 2 electrons and we're going to add them to the 2 bromines to make 2 Br- anions. So we've combined the electrons with the nonmetal to make the nonmetal anions. This step here, we have 2 bromines each gaining 1 electron, so that's going to be 2 times the electron affinity. Electron affinity is the energy required for 1 bromine atom to gain an electron. This time we're doing it twice, so we have to double that number. The electron affinity for bromine is this number here, minus 331, and so we have to double that in this step. So 2 times that, or minus 662 when we have 2 moles of bromine gaining 2 electrons to form 2 Br minuses. And then finally, the last step, now that we have the gas phase ions, is to recombine them into the solid. That's, again, the lattice enthalpy. All right, so once again, the sum of all of these steps as we go around the cycle has to equal 0, and the only unknown is our lattice enthalpy once again. All right, so this whole thing set equal to 0. We have 524, which is the first number down here, plus 148, plus 2187, plus 31, plus 193. Those are all the endothermic steps, and then we have an exothermic step of minus 662, plus lattice enthalpy. All of those added together equals 0. All right, so it's in this case 7, I think, instead of 6 terms, but they all sum together to equal 0 still. And then when we solve for lattice enthalpy, we should get minus 2421 kilojoules. When you're doing problems like this that ask you to find lattice enthalpy should always be a negative number. So if you get something that's not negative, you might want to check yourself, or I would say you definitely want to check yourself. But again, it's going to be some variation on this theme of going around this whole cycle. Now, some people don't like to have to draw out this cycle every time they do one of these problems, or some people don't quite follow it. So there is a relatively general equation that works that I'll give you. I don't know if I should put it on a separate page. Probably should, if I can figure out how to do that again. I'm going to add an extra page and do this, because I don't want to confuse this with what we were doing before. How does it full screen? Page. Alright, so I added another page into here just so we don't put this on the last stuff. Okay. So what I'm going to call this is, in quotes, a general equation to solve for lattice enthalpy. As I said, there could be some slight variations on this. And this works for when you have an ionic compound with a formula M with a subscript of M and X with a subscript of X. So these tell you the number of metals and nonmetals in the formula. They're going to be 1s or 2s. We're talking about, binary ionic compounds, pretty simple things like sodium chloride, or in the last case, magnesium bromide, which is 1 to 2, or you could have a 2 to 1 like sodium oxide. So different combinations of metals and nonmetals in the correct formula. And also this equation works if X2 gas is the standard state for the nonmetal, which is true for most nonmetals. So F2, Cl2, O2, all of those are diatomic gases. Those are the most common ones we'll see. If your nonmetal has a different standard state, as we saw for Br2 liquid, you had to have another step associated with putting it in a gas phase sometimes, depending on how the information is given to you. Or if your nonmetal was sulfur, sulfur exists as S8, so there'll be some differences there that I'll point out. But this works for most ionic compounds. And so what it comes out to is when you put all those steps in that we use to build this cycle and solve for lattice enthalpy, it's going to be the only term that you don't change the sign of is delta H of formation when we solve for it. So that's for the ionic compound itself, the delta H formation. We put that in as given to us. And then we're going to subtract 2 terms that are associated with the metal, and we're going to modify them by the subscript here, which tells us how many moles of metal we have in our ionic compound. So the first one, as we said, is sublimation enthalpy for the metal. The second term for the metal is going to be its ionization energy. And again, if it's a 2+ metal cation, it has to be 2 ionization energies added together, which we'll very often give you as just one number. So those are the 2 terms associated with the metal. And so then the next 2 terms are going to be associated with the nonmetal. So you have to do the dissociation of the nonmetal diatomic, which is going to be, in this case, X over 2 times the bond dissociation energy, or X2, if X2 is the standard state. And then finally, the next step associated with the nonmetal is going to be its electron affinity, which you modify by the number of nonmetals in the formula X. Alright, so this equation will work most of the time. As I said, there's some times when it won't, so you want to try to understand this in the full detail that I've given it to you. For example, if it was something besides X2, if it was S8, for example, with sulfur, it would be X over 8 if we're giving you the dissociation enthalpy of S8, or there's other ways to present that information. So you have to be familiar with some of the variations and some of the concepts behind this, but this type of equation will work in most cases, and these are all the different steps that then go into it. Okay? Alright, so any questions on this topic before I move on? Probably are, but we can... Yeah, sorry. Yeah, so this is the ionization energy of the metal itself. So sometimes in these problems we'll also give you extra information to really see if you understand this. So you don't need the ionization energy for the nonmetal. If we give you the ionization energy for X, whatever the nonmetal is, you leave that out of the calculation. You only need the ionization energy for the metal itself. So these 2 terms here are associated with the metal, and these 2 terms here are associated with whatever the nonmetal is in the chemical formula for your ionic compound. And that's how we're going to use those. Yeah? Yes, because the way we set up the cycle is actually the negative of that, but then when we solve for lattice enthalpy, it becomes positive. Because remember, this is negative delta H formation, but then we're solving for this, and that moves over to the other side and becomes just delta H formation. So yeah, you'll always use, if you're solving for lattice enthalpy and using this equation, it'll just be delta H of formation as given to you, not modified by any coefficient, not change the sign ever. Okay? Anything else? Alright, so that's how we calculate lattice energy. The last thing we're going to talk about is one other type of problem we'll ask you to do related to lattice energy is sort of comparing lattice energies for different ionic compounds. And this is pretty straightforward to do. So here you wouldn't be necessarily calculating the exact the exact lattice energy for all these different compounds. You're just trying to compare one to the other, relatively speaking. So from basic physics, what happens is that the lattice enthalpy is equal to some constant times the two charges multiplied together divided by the distance of separation between them. Alright, so Q1 and Q2 are the charges of the ions in the compound. And as I said, it's going to be either +1 and -1 or +2, -2 or some combination of those. We're talking about just simple binary ionic compounds. So those are the charges, and then R is going to be the distance between them when they pack together into the ionic compound. So these are the two factors. And as I said, we're not going to calculate lattice energy in this way. We're going to use this concept to compare lattice energies of two different compounds. So there's two parts, as we said. There's larger ions and there's higher charges. So if we have larger ions, so we learned about how to compare ionic radius also back in chapter 3, so that concept comes back here as well. If the ions are farther apart, that means that this radius term here gets larger. So when you have larger ions in the formula, they're going to be farther apart from each other. So if we're comparing F- to Cl-, F- is smaller than Cl-, and it would pack closer together to the positive ions. So the larger ions are going to be spread farther apart from each other, and that's going to result in a smaller lattice energy. And when we say smaller, we mean less negative. So we're talking about the magnitude of the lattice enthalpy here. All right, lattice enthalpy is always negative, and when we say smaller or bigger, we're talking about either more or less negative. All right, so smaller lattice energy is a less negative value, and that's what happens when you have larger ions. And then if we increase the charge of the ions, that's this Q1, Q2 term here, the product of the charges, that will then be directly related to the lattice enthalpy. Which means a more negative or larger lattice enthalpy when you have more charge in your ions. And so if you look at the examples we did above, MGBr2 and KCl, we saw that the lattice enthalpy for MGBr2 was much larger than KCl, and that's because it's a 2+ cation instead of a 1+ cation. So when we're making these comparisons, we're going to do one example here in a second. The first thing you want to look at is the charge, because that's, and it turns out, the factor that's more important. Because if we change the charge from a +1 -1 compound like sodium chloride to a +1 -2 compound like MgO, magnesium oxide, this term here changes by a factor of 4. So that's a huge effect. The radius term down here is never going to be that large of a difference. So even if we're comparing the smallest ions on the periodic table to the largest ions in the periodic table, the difference in their distance apart is not going to be anywhere close to a factor of 4. It's going to be a much smaller amount than that. So when you're comparing lattice energies, look at the charges first, and then if you have a series of compounds with the same charges, then go and start comparing the radii and determining which one has the smaller or largest lattice enthalpy. All right, so as an example of this, let's say we have this list of compounds: sodium fluoride, lithium fluoride, magnesium oxide, magnesium sulfide, beryllium oxide. We want to look for which one has the largest or most negative lattice energy. Again, the concept for all of these types of problems where we're comparing lattice energy is that this is going to be proportional to the product of the charges divided by the distance between them. Okay? And then what I also said is it's important to look at the charge first, and then we start comparing the sizes of the ions involved. Okay, so we're looking here for the largest lattice energy, so we're going to look for the ones that have the highest charges first. So if we think about the charges, sodium fluoride is a +1 -1 ionic compound. Na forms +1 cations, fluoride is -1 anion. This one is also +1 and -1. And then these last three here, magnesium oxide, magnesium sulfide, beryllium oxide, these are all +2, -2 ionic compounds. The cation is +2, the anion is -2 in all of these. So if we're looking for the largest lattice energy, we're going to choose from the ones that have the highest charge, so we can eliminate choices A and B. Okay, so if we're looking for, as I said, look at these comparing the charge first, then the radii. So we look at the ones with the largest charge, and then we just have to compare these three to each other and figure out which one's largest. So if we compare magnesium oxide to magnesium sulfide and determine which of these has the ions closer together or further apart, they both share the magnesium 2+ cation, so that part of it's the same, but then this one has the oxide anion and the sulfide anion. If we go to the periodic table, if we want to refresh how to do these comparisons, on the periodic table here, oxygen is above sulfur, so that means oxygen is smaller than sulfur, which means the oxide anion would be smaller than sulfide. And so that means if O2 minus is smaller, the magnesium and the oxygen are going to be closer together. That's going to have a smaller radius, and that would give you a larger lattice enthalpy. So comparing these two, we can conclude that magnesium oxide is larger than magnesium sulfide because O2 minus is smaller than S2 minus, and that means that these ions are packed closer together. And then if we compare the last two, magnesium oxide with beryllium oxide, they have the same anion in this case, but different cations. And so if we compare beryllium to magnesium, in this case, beryllium is above magnesium, so beryllium is going to be the smaller cation, which means that beryllium and oxygen get closer together. So we're comparing ionic radii here, which is basically the determination of how close they're going to be together. And so beryllium oxide has a smaller radius. The two ions are closer together, so the radius here is in the denominator, which makes the lattice energy smaller. So beryllium 2+. Smaller than magnesium 2+. So that means this one here is going to be our winner because it has the highest charges and it has the combination of the smallest ions that pack closer together and give the smallest radius here. So that's how we compare lattice energies. That's the only other type of question we would ask you about lattice enthalpy besides using the Bornhaber cycle to solve for it. Question? So LiF and NiF, lithium is smaller than sodium. It's above it on the periodic table. So these two would get closer together. This one would have, and lithium fluoride would have the larger lattice enthalpy of those two. So that means of these five, sodium fluoride would be the absolute smallest, and then lithium fluoride, and then the rest of them that we ranked in that order for the 2+ compounds. So like I said, look at the charge first, but if you have two that are same charge, you have to compare the size of the ions that are in those compounds, which comes from the periodic trends for ionic radius that we also learned back in Chapter 3. All right, any last questions on this? All right, so that takes us to the end of everything that's related to Chapter 7. What we're going to move to next is Chapter 8. So I'll write that up here in case you're following along. We're on to Chapter 8 now. And before we start, so Chapter 8 is all about gases. And we're going to talk about, first let's review what the states of matter are. Because what we're going to deal with in Chapters 8 and 9, the last two chapters we're going to do in this course, are going to be the different states of matters and some of the properties and things associated with them. So the three states of matter, as I'm sure we're all familiar with, are solid, liquid, and gas. Chapter 8 deals with gases. Chapter 9 deals with the other two. All right, so let's just talk about the differences between these. Solids have a fixed volume and shape. And then if we go to liquids, liquids have a fixed volume, but the volume conforms to the container. So the shape of the compound is not fixed in this case. So depending on what container we put it in, this volume is going to have a different shape associated with it. And the other important thing about a liquid is that it does have an upper surface. So it doesn't just spread out everywhere. It has an upper surface, but its shape is not well defined. And then the gas, which is the last phase of matter, which is what we're going to talk about in this chapter, a gas completely fills its container. So if we take a small amount of gas, like in a balloon, and we pop it here at the front of the room, the gas that was in that balloon is going to spread out over the entire room over some period of time. Not immediately, but over some period of time it will occupy the entire room. It's not fixed to any one location. It's freely flowing. And they tend to have low density because the molecules end up being spread apart very far. So these pictures here sort of show you the molecular level differences between these. This is water, gas, solid, and liquid water. So in the solid phase, the water molecules, and we'll learn more details about this in Chapter 9, they're all really close together. and there's very little motion of them, and they're all kind of stuck in place, and that's why the solid would have a fixed volume and shape. In liquid water, the molecules are moving around, but they're in contact with each other, so they're kind of rolling over each other. They can flow, they can change their shape very easily, but they're all kind of stuck together still, so they have a fixed volume and an upper surface. And then in any gas phase sample, like water vapor, for example, they're going to be bouncing all over the place. So the molecules have really no association with each other. They're bouncing around, randomly distributed. And those are the details we're going to cover then in this chapter, the properties of the gas phase in particular. So the first thing we want to talk about is an important property of gases, which is called pressure. Now, we did introduce this a little bit in Chapter 7 when we talked about expansion work, which is the ability of gases to expand and do work. So pressure is defined, as we said, as force divided by area. And because gas molecules are moving around rapidly throughout space, whenever you have a contained sample of gas, it's going to exert a pressure on the walls of those containers. And so let's first talk about how we measure the pressure. So the first thing we're going to talk about is a barometer, which measures atmospheric pressure. So you've probably seen barometer readings in the weather reports sometimes. So the way we measure those is with a barometer. And so this is what we use to measure atmospheric pressure. So if the weatherman says, or the weather person says there's a low pressure system going through, that means that the air pressure in that system is lower than what we had before, and so on. They measure it with a barometer. So the way a barometer works is you have a closed glass tube, and then you invert that into this is a very low-tech barometer, but it's inverted into a plate of mercury. So mercury is a really high-density liquid. We use this often for measuring pressure. And so what happens is that the atmospheric pressure pushes down on the plate of mercury, and it forces some of it up into this tube here. Okay, so it's just, and then it's going to, basically the motion of the mercury stops when the two forces are equal to each other. So you have the force of the mercury pushing down because of gravity, you have the force of the gas opposing that, and those two are going to equalize each other until the mercury is at some level here in your barometer. Now there's some math that goes into this that I'm not going to derive and you're not going to be responsible for, but it turns out that when we're using a barometer or any sort of pressure measuring device, the pressure is directly related to the height that the mercury goes up the column. So whether we had a really thin column of mercury or whether we had a column of mercury that was as big as a tree trunk, all that we need to measure the atmospheric pressure is the height that column goes. It doesn't depend on how wide the column is, it just depends on how high the column is, and that will give you a direct measurement of the pressure. So when we measure atmospheric pressure, it corresponds to around 760 millimeters of mercury. Now that number can of course change a little bit depending on the atmospheric conditions, but standard atmospheric pressure at sea level is 760 millimeters of mercury. So if we have a mercury barometer at sea level, the height of that mercury column would be 760 millimeters. And the reason we use mercury, not water, is because if we use a lower density liquid like water, the height of the column would have to be 34 feet. Okay? So barometers would have to be about the size of a 3-story building to be able to use water in them. So that's not a very practical way to set up a barometer. So we use mercury because it's much more dense and gives you a column height that's roughly this high off the table, not unreasonably tall. All right, so that's how we measure atmospheric pressure. Then the other device that we use to measure the pressure of a gas sample is called a manometer. So there's two types of manometers, which are illustrated here, kind of small, but if you have the notes you could probably see them, and I think the pictures like this are also in your book. So one type is called a closed-end manometer. And as the name suggests, we have this sort of U-shaped mercury column here. So what you have is your gas is going to push on this mercury column, and it's going to create a height imbalance between the two sides. But this end of the tube here is completely closed off. And so what that means is that there's no pressure that's opposing the other side. There's no gas on the other side. It's evacuated. So what you're measuring here is pressure relative to a vacuum. And because there is no pressure pushing down on the other side of the gas, of the other side of the column, this difference in height between the two sides, this term here, the difference in height between the two is just equal to the pressure directly. All right, so you just measure the height difference between the two sides of your column, and that gives you the pressure of the gas in millimeters of mercury. Now, the other end is called an open-end manometer. So in this case, we have a sample of a gas, but the difference here is that we have atmospheric pressure pushing down on the other side. So this end of the manometer is now open up to atmosphere, and so you have atmospheric pressure pushing down on one side, the sample of your gas pushing down on the other side, giving you this delta H, this difference in height between the two. So in an open-end manometer, you're measuring pressure relative to the atmospheric pressure. And so the pressure of the gas is equal to the atmospheric pressure plus and minus the difference in the height between the two columns. All right, so again, you're measuring a height difference between the two columns that the mercury fills, and it's going to be the atmospheric pressure plus and minus that height difference. So if the pressure of the gas is smaller, as we have here on the left, that means atmospheric pressure is pushing down harder, and you're going to have a height imbalance in this way where the mercury is lower on the side of the atmosphere. If the pressure of the gas is higher than atmospheric pressure, you would have a situation where the pressure of the gas pushes down harder, the mercury column is lower on this side than it is on the atmosphere side, and then your gas pressure would be higher by that amount. So depending on which of these situations you have, you're either going to add or subtract the height difference between the two sides. And it depends on whether the gas pressure that you're measuring is higher or lower than atmospheric pressure. So you're always measuring relative to that. All right, so that's how we measure pressure. So for this open-end manometer, you would have to use a barometer to measure atmospheric pressure, and then the manometer to measure the pressure of the gas indirectly relative to that. So that's how we measure pressure. Let's talk a little bit about the units for pressure. So the SI unit for pressure is called the Pascal, abbreviated PA. Now, as it turns out, this is a pretty small unit of pressure relative to the typical pressures we use for gases. So 1 Pascal is equal to 1 Newton per meter squared. So these are the SI units for force and area, newtons and meters squared. And we can break that down further into SI units if you're a units buff. This is kilogram meters per second squared. So these are all the SI units, and it's called a Pascal. But it's a pretty inconveniently small measure of pressure. So the one that we use most often in this course is going to be atmosphere, abbreviated ATM. And this is basically the 1 atmosphere is the average atmospheric pressure at sea level. Or we can call that the barometric pressure, now that we know what a barometer is. So this is the most common unit of pressure that's used in chemistry, or at least in the types of chemistry things we're going to talk about. And so the relationship is that 1 atmosphere is 101.3 kilopascals, or 1.01 times 10 to the 5th Pascal. So as I said, a Pascal is a very small unit of pressure. It's basically 1/100,000th of an atmosphere. So it's not a very convenient one. We use atmospheres more conventionally because those are the pressures that we deal with when we're talking about, well, the atmosphere itself or samples of gas that we're working with in the laboratory are typically some multiple of 1 atmosphere. Now there's another pressure that I don't think we'll use a lot, but we should be familiar with, which is bar. So bar is basically based on the SI units, and so it's going to be just 100,000 pascals is 1 bar. All right, so this one is very similar to an atmosphere, has almost identical size of unit as an atmosphere, but is based directly on the SI unit of 1.013 times 10 to the 5th Pascal being 1 atmosphere. So these are the two. So there's really two units of pressure though that are most common. It's going to be the atmosphere and the torr. So the torr is based on the height measurement using a mercury column. So 1 torr is equal to 1 millimeter of mercury. So these two are going to be used interchangeably. So you'll either see it as torr or as mmHg. They mean the same thing. And the conversion factor that you should definitely be familiar with, because it's one that you'll use all the time, is that, as we said, atmospheric pressure is 760 millimeters of mercury, which means that 760 torr is equivalent to 1 atmosphere. So it's this conversion that we'll have to use a lot, because pressure is often measured in torr, because that's millimeters of mercury. That's the height of the mercury column when you use a manometer or a barometer to measure pressure. But we often report it, or we use equations that are in terms of atmospheres, so we have to be able to convert between the two. All right, so those are the two units of pressure, torr and atmospheres. That's the numerical relationship between them. So let's just do one quick example of how we convert units of pressure. So if we have a compressed gas cylinder, they're usually supplied at 2,000 psi, which is a different unit of pressure that we don't use a lot, but we should we see it here. 1 psi is 1 pound per square inch. So this is like the English unit for pressure, the one that they use a lot of times in the UK and the United States, because we refuse to adopt the metric system. All right, so psi is 14.7 psi, 1 atmosphere. 1 atmosphere, as we said, is 760 torr, and we just want to be able to convert these two. So if we're looking for the pressure in millimeters of mercury, our given pressure is 2,000 psi. So this is just unit conversions. We should be pretty familiar with this now. And the way we can do this is we know that we have a relationship between atmospheres and psi. So 1 atmosphere is 14.7 psi. And then if we want to go into millimeters of mercury, we know that 1 atmosphere is also equivalent to 760 torr. And then 1 millimeter of mercury is equivalent to 1 torr. So in a trivial conversion, we can convert torr into millimeters of mercury, because those are equivalent units, as we said. And so what this comes out to is 1.03 times 10 to the 5th millimeters of mercury, which is approximately equal to 100 meters of mercury. All right, so this was just a simple example of unit conversions. The other thing it shows us indirectly is that if we wanted to measure the pressure inside of a gas cylinder, we would need a mercury column that was 100 meters tall, which is about 390 feet tall, or no, sorry, 310 feet tall. So what this shows us is that these mercury manometers, mercury barometers, are not very convenient for measuring really high pressures. So for measuring high pressures, we have much more sophisticated devices that do that. We won't talk about the details of those or their engineering, but keep in mind that these mercury columns, these sort of low-tech pressure measurement devices that are very common in chemistry, are usable for relatively small pressures. But if you go up to really high pressures, you would just need way too large of a column to be able to accurately do that. All right, so let's now talk about then relationships between different properties of gases. So we hopefully understand what pressure is and how to measure it. Let's see how the pressure is affected by different parameters. So if I can do this efficiently, we're going to pull up some videos. So the first thing we're going to talk about is Boyle's law, which is the relationship between pressure and volume. And I should have pulled these up before class. I hope that I can find them quickly. All right, so Boyle's law demonstration. All right, so what they're going to do here is they have, and a lot of gas law demonstrations are done with balloons. For some reason, not letting me maximize this. All right, paused. All right, so we have a balloon, and what they're doing is they're evacuating the container. So they're reducing the pressure inside of here, and we see that the volume of the balloon gets larger. So when they reduce the pressure, the volume gets larger. So that would suggest that there's an inverse relationship between pressure and volume. Pressure gets smaller, volume gets larger. So that's what they're doing, is they're evacuating the container, removing and lowering the pressure. And then when they allow air to go back into the container, we see that the pressure raises and the volume of the balloon then gets smaller. Now they're going to do the same experiment with a marshmallow peep, which is also filled with a lot of gas. And so they're going to tighten this on there, and they're going to evacuate the container to lower the pressure inside of there, and we can see that the peep grows larger and larger. And then when he lets it back in, it's not totally reversible because the structural integrity of the marshmallow has been compromised by doing this, but you can see that the volume shrinks once the pressure increases. And now with some shaving cream, he'll do the same thing. So a lot of air is trapped inside of shaving cream. When you lower the external pressure, the volume of the gas inside the shaving cream increases, and we see that it goes everywhere as the pressure gets lower and lower. Okay? So what these experiments demonstrate to us is that there's an inverse relationship between pressure and volume. When the pressure gets smaller, the volume gets larger. When the pressure gets larger, the volume gets smaller. All right, so that's a demonstration of what's referred to as Boyle's law. And that's where we have a constant temperature, but we're changing the volume and the pressure. And so what Boyle's law tells us is that volume is inversely proportional to pressure, or volume is proportional to 1 over the pressure. So volume and pressure are inversely proportional to each other. And then if we want to write this as an equation, we could say that volume is equal to some constant divided by pressure, although this constant is poorly defined because it depends on a lot of different things, as we'll see. But we can rearrange this and say that pressure times volume is equal to a constant for that specific gas, as long as we keep the temperature the same and we're not changing the amount of gas that we have. Which means, as we saw, if we have something that's set equal to a constant, we can take the initial and the final states and then set them equal to each other. So P1V1 is equal to some constant. That's going to be equal to then P2V2. So this is another way to state Boyle's law as an equation. P1V1 equals P2V2. So if we have a sample of gas at some pressure and some volume, if we change the pressure or the volume, the system is going to respond in such a way that we can calculate using this relatively simple equation. So this is referred to as Boyle's law. It's the relationship between volume and pressure. Now the next gas law we have, let's do a quick example problem with this before we get to the next one. Got ahead of myself. So let's say we take a balloon and we inflate it to a volume of 0.5 liters at sea level. So at sea level, then the pressure is going to be about 1 atmosphere. If the balloon rises to an altitude of 6.5 kilometers, where the air pressure is now lower at 0.4 atmospheres, what will its final volume be? So we're going to ignore other little factors like the balloon's elasticity and just assume that the balloon is able to expand and contract readily under responses to change in pressure. So again, Boyle's law, we're just changing pressure and volume here. P1V1 equals P2V2. And so what we're solving for here is the final volume, V2, which is just going to be equal to P1V1 divided by P2. So the ratio of the two pressures times the initial volume. So P1, we're saying that we're starting at sea level. So we're not telling you P1 directly, but we mean if we're at sea level, that means P1 is approximately equal to 1 atmosphere. So that's our initial pressure, 1 atmosphere. Our initial volume is 0.5 liters. We can use any unit we want here because we're just solving as a ratio. 0.5 liters. And then the final volume would be, the final pressure, P2, is 0.4 atmospheres, which goes down here. And then this comes out to 1.25 liters. Okay, so the volume of the balloon expands when the pressure of the atmosphere around it is lower. All right, so pressure and volume are inversely related. This is the equation, and it's relatively simple to set up and solve. And this is what we would call Boyle's law. All right, the next gas law we're going to talk about is called Charles' law, and we have a video for this one as well. A short video. Oh no, this one's not showing up in my history. Let's see. It's this one, right? Alright, Charles' law example. So we have a balloon here, and we're putting it into liquid nitrogen, so we're making it a lot colder. Why doesn't this one stay full screen? Come on. And you can see that the balloon is shrinking as the temperature gets lower. Alright, so the volume of the balloon gets smaller when the temperature is also getting smaller. So that would suggest that volume and temperature are directly related. When one gets smaller, the other also gets smaller. Now if we remove the balloon from the liquid nitrogen and allow it to warm back up, this guy's lack of safety equipment is a little bit alarming, but the point still stands that as the balloon warms back up, the volume gets bigger. So that would tell us when the temperature goes up, the volume also goes up, meaning that volume and temperature are directly related to each other. Okay? So Charles' law tells us that volume is proportional to temperature. So volume is directly proportional to temperature, specifically. which means volume is equal to some constant, which I'll abbreviate as K prime, because it's not the same constant as the last one, and there isn't, as I said, no defined constant times temperature. But we can set this up in terms of initial and final conditions, where V1 over T1 equals V2 over T2. Okay? So we just set them, we just rearrange everything, move it all to one side, and we set the initial and final equal to each other. So that's a mathematical expression of Charles's law. Okay? Now we have to be careful with units here. And when we're going into gas laws with chapter 8, moving on from chapter 7, the temperature must be in Kelvin for all of these problems. All right, in chapter 7 we were always doing differences in temperature, delta T, when we're calculating Q, for example. And when you're doing delta T, you can have either Celsius or Kelvin because the difference in the two temperatures will be the same. When we're doing anything with gases where we're using the absolute temperature, which is just T by itself, not delta T, anytime you're using absolute temperature, it has to be in Kelvin. And as a reminder, the temperature in Kelvin is equal to the temperature in degrees Celsius plus 273. Oh no, don't crash again. Good. And if you're being really precise, it's plus 273.15. Alright, so we have to be able to convert Celsius and Kelvin, and when we're doing problems with gases, we have to always use the Kelvin temperature, the absolute temperature. Alright, so those are the first two gas laws, and then the last one we'll talk about is Avogadro's, but let's do Charles' law first, a quick example problem. So let's say we have a sample of gas that has a volume of 79.5 milliliters at 45 degrees Celsius. What volume would it occupy at 0 degrees Celsius if the pressure were held constant? Alright, so here we're changing volume and temperature, so that relationship is called Charles's law. And some of you might be wondering why I'm calling it Charles's law, not Charles' law. As someone whose last name ends in an S, I'm acutely aware of that. A pluralized last name that ends in S would also add an apostrophe S, so it's Charles's, not Charles. So now that I've taught you some grammar, we can move on to chemistry. So V1 over T1 is equal to V2 over T2. That's Charles's law. And so what we're solving for here is the volume at the new temperature. So we're solving for V2, which is V1 times T2 divided by T1. And again, the caution here when we're using temperature as part of our calculation is that it has to be in Kelvin. So our initial temperature is T1, 45 degrees Celsius. We have to add 273 to that to get the temperature in Kelvin, which is 318. As I said, it's 273.15, but for these types of problems, if you just do 273, you'll be fine. And then T2 in Kelvin is 0 degrees Celsius, and we have to add 273 to that to get it in Kelvin. Okay? Now this should hopefully make it obvious, because if we would have put T2 in as 0, we would have gotten an answer of 0, and the volume, of course, doesn't go to 0 at 0 degrees Celsius. So the temperatures have to be in Kelvin in the absolute units. So now we just have to plug the numbers in, and we get 79.5 milliliters. 273 Kelvin is our T2 that goes on the top of this equation, and then 318 is T1 in the bottom, and that comes out to 68.2 milliliters. Alright, so as we saw in that video, if we decrease the temperature, we should also decrease the volume. And by decreasing the temperature from 45 degrees to 0 degrees Celsius, the volume decreases from almost 80 milliliters down to 68. So not a huge change in volume, but a relatively small change in volume. Alright, last gas law I'll talk about individually is Avogadro's law. This one I don't have a video demonstration of, but I think it's probably the most intuitive one. So Avogadro's law deals with the relationship between the volume and the number of moles. We introduced this a little bit in Chapter 1 when we talked about some of the early experiments that were done to determine chemical formulas, and Avogadro was an important part of that. He also has a number named after him, but that's not really his claim to fame. It's really this thing that he came up with. And his law is, I think, the most intuitive of them, which is that if we add more moles of gas to a sample, is the volume going to get bigger or smaller? Bigger. I think that should hopefully make sense to us. If we add more gas, the volume of the gas expands. So volume is proportional to number of moles, which means, again, if we want to write this as an equation, volume is equal to some constant times the number of moles, or more conveniently, setting two initial and final conditions equal to each other, V1 divided by N1 equals V2 divided by N2. Alright, so this is the mathematical statement of Avogadro's law, which is that volume and number of moles are directly proportional to each other. If you have more moles of gas, you have a larger volume, and they're related in that way. Okay? So that's the last individual gas law, which is Avogadro's law, so we'll do a quick problem with it. Let's say we have, at a certain temperature and pressure, we have 28 grams of nitrogen, which has a molar mass of 28, and it has a volume of 20.8 liters. How much volume does 40 grams of oxygen occupy at the same temperature and pressure? So here we're talking about two different gases, but we're looking again at relationships between their volume and their number of moles. And the other important thing that we're starting to see here in this problem is that when we're talking about these gas laws, the identity of the gas doesn't really come into play. It's just, again, its volume, its temperature, its pressure, and its number of moles. Those are the four important parameters, but what gas it is doesn't really matter. Okay, so this is one here where, again, we're relating volume and number of moles, and we're solving for what the volume is of O2, the second volume here, so we can call that V2, although we could, of course, set it up either way. So it's going to be V1 times N2 over N1. So the volume of the N2 is 20.8 liters. And we just need the two number of moles to figure out what the volume of the sample of O2 is going to be. So N1 is the volume of nitrogen that we're considering, which has a volume of 20.8 liters. So that's going to be 28 grams of N2 times 1 mole of N2, which is 28 grams per mole. So that's 1 mole of N2. So just converting mass into moles. So that's going to be the bottom here. That's our initial number of moles, 1. Then we want to know how many moles does the sample of oxygen include, which we're going to have to then multiply here to get the volume of that sample of oxygen. So N2 is the moles of oxygen. So we have 40 grams of oxygen. The molar mass of O2 is 32. And so that 40 grams of oxygen corresponds to 1.25 moles of O2. And so that's the amount of moles that we're putting up into this part of the equation. And this means that this sample of oxygen would occupy a volume of 26.0 liters. So it doesn't matter that we're comparing two different gases here. The relationship between volume and number of moles is still the same for both of those gases. And so if we know the number of moles of volume of one of the gases, we can find the volume of the other sample of gas as long as we know how many moles of that one we have. So that takes us to the end of the individual gas laws. What we're going to learn next time is how we can combine these three gas laws into one, and that's going to be the one that we're going to then primarily use as we're doing problems related to the properties of gases.